This time, I'm going to talk about Variance Gamma process in Python. The Variance Gamma process is a type of Lévy process used in mathematical finance and stochastic modeling. It extends Brownian motion by introducing jumps, allowing for skewness and excess kurtosis in asset return distribution. This is the formula for Variance Gamma process. Here, Wt is the standard Brownian motion, and Gt is the gamma process with a mean rate 1 and variance rate mean. Theta represents the drift of the process. Sigma represents the volatility. Again, mean is the variance of the gamma process. Let's take a look at the key properties of Variance Gamma process. The Variance Gamma process is a Brownian motion time changed by a gamma process, making it more flexible in capturing financial asset dynamics. Unlike a standard Brownian motion, it allows for skewness and excess kurtosis. Another name call it is fat tails, which better match financial return distributions. Like Brownian motion, the increments are stationary and independent. If used for risk-neutral pricing in finance, the drift term theta is adjusted to ensure that this item remains a Montingo. Okay, here I list the comparison between the Variance Gamma process and Merton Jump-Diffusion process. And you can take a look, and I will not go through each item one by one. And I just want to talk about the intuition behind the differences. First, let's take a look at the jump structure. In Variance Gamma process, jumps are continuous and small, occurring infinitely, often due to gamma subordination. This creates heavy tail distributions similar to real asset returns. When we check out our model, you can see this heavy tail clearly. In Merton Jump-Diffusion process, jumps occur at discrete random times following a Poisson process. These jumps are normally distributed, meaning that MJD captures large, infrequent shocks to prices, such as earnings surprises or financial crashes. Second item, let's take a look at the volatility handling. The Variance Gamma process allows for stochastic variance, meaning that the price fluctuations are controlled by a gamma process, not constant time. The Merton Jump-Diffusion process retains a traditional Brownian motion for diffusion, but superimposes discrete jumps. When we use those processes, Variance Gamma process is used for option pricing and risk management, especially in models that require smoothed, non-Gaussian returns with continuous jumps. On the other side, Merton Jump-Diffusion process is better suited for markets where crashes and rare large events play a crucial role. So, how to choose your model? If you need a process with continuous, infinite jumps that naturally models skewness and heavy tails, then variance gamma process is a good choice. If you need rare large jumps combined with standard Brownian motion diffusion, then mergent jump diffusion process is preferable. Now, let's go to Python to check out our model. Okay, so in our model, first we will give some initial value for our parameters, and then we use this function calculate variance gamma density, and this function is a characteristic function of our variance gamma random variable. About characteristic function, I already explained in my previous video. If you haven't watched that video, you are welcome to watch that video as well. And then we use this function to calculate Gil-Pelaez PDF inversion, and then we will draw variance gamma histogram. And after that, we will draw a QQ plot, check the distribution. Okay, now let's run our model. You can see this is our variance gamma histogram. The x-axis represents the range of observed value from the variance gamma process, and the y-axis represents the density or frequency of occurrences. And you can see this histogram, the light blue region, represents the empirical frequencies of a sample of values drawn from a variance gamma distribution. And this red line is variance gamma density. This is a theoretical probability density function of the variance gamma distribution. Those blue dots is Fourier inversion. That represents numerical values obtained using Fourier inversion. You can see all those histogram or those variance gamma density and the Fourier inversion, they match perfectly. Next, let's check out the QQ plot for this variance gamma process. The x-axis is the theoretical quantiles, and the y-axis is the sample quantiles, represents the quantiles from the empirical sample of the variance gamma process. And the blue dots is empirical data points. Each point represents a corresponding quantile from the theoretical and the sample distribution. And you can see this red line is a reference line for normality check represents where points should fall if the sample perfectly follows the reference distribution. So you can see this curve shows like this is not following the red line. That indicates skewness, meaning the distribution is asymmetric. The variance gamma process can generate both skewness and kurtosis, which explain this behavior. In conclusion, the variance gamma process does not follow a normal distribution, but instead has heavier tails and potential skewness. Lastly, in our model, we use this MRE method to estimate all those parameters. We have an initial parameter here, and we have this MRE parameter here. You can compare all those parameters are pretty close. This is how you can build variance gamma process in Python. Please comment, like, and subscribe to my YouTube channel. Thank you for watching.